This is a story that goes back many decades to the beginning of the Apollo program, and it's in fact a science story that goes back thousands of years. And I'm a very small part of this exciting story to bring new special optical instruments called retroreflectors to the surface of the moon. So the moon is our nearest celestial neighbor, as everyone knows, and it's drawn the eyes of humanity and minds of scientists across the world for millennia. Now, the current leading theory about the formation of the moon is that a Mars-sized planet named Theia collided with the primordial Earth roughly 100 million years after the formation of the solar system. So this was about 4.4 billion years ago. And the image on the left there is an artist's rendition of what this may have looked like. Now, when this impact happened, material from the Earth and Theia were mixed together, and as the debris cooled, they were drawn together to form gravity, and formed the moon in orbit around the Earth. Now, what this Theia was, how and when it impacted the Earth, and how the material was transferred between the primordial Earth and the moon all have immense implications for the formation of life on Earth, which occurred several hundred million years after this impact event. Now, the size of the moon compared to Earth and the distance between the Earth and the moon both affect the strength of the tides on Earth, which also has profound impact on the development of our planet through the action of plate tectonics and continental drift, as well as an impact on our human culture across the millennia. So today I'm going to tell you the story about how we calculated the distance to the moon, the special tools we used to do it, and how all of these same techniques to operate around the moon and on the surface for future exploration will be used for generations to come. So as I mentioned, the distance between the Earth and the moon and the celestial dance between these two bodies in relation to each other has been of immense scientific interest for thousands of years. The moon is the most obvious and easily discernible object in the night sky, and the patterns of its movements as it changes throughout its 28-day orbit around the Earth can be tracked even today by a precocious kindergartner. Our written records of observations of the moon and its many phases go back to Babylonian astronomers in roughly 1000 BCE called the Mulapine tablets, which are shown on the left there. The next major advance came with the explosion of Greek philosophy and science in the 4th century BCE, and that includes primarily the work of Aristarchus of Samos, who used key observations to calculate the sizes and distances between the Earth and the moon in terms of the Earth's radius. And he did this by using 3 measurements. The first one was the apparent size of the moon and the sun in the sky. The second was the size of the Earth's shadow in relation to the moon during a lunar eclipse. You can see that on the left-hand side there. And finally, the third is the angle between the sun and the moon during a half moon, which is shown in the upper right there. Now, what he did was he assumed that the sun and the Earth and the moon formed a right triangle during a half moon. He calculated the ratio of the distance between the distance to the sun and the distance to the moon as roughly about 20. And then he assumed that because the size of the sun and the size of the moon are about the same size in the sky, that the sun must be 20 times larger than the moon. He was off by about a factor of 10. That was mostly due to his incorrect value for the size of the sun and the moon in the sky, which was actually improved upon later by Hipparchus and also Ptolemy. So these were primarily the best ways we had of measuring the distance between the Earth and the moon for thousands of years. These were called optical angle measurements, and they continue to be improved upon by things such as lunar parallax, which is observing the angle between the moon and a chosen reference point from multiple locations, something called meridian transits, and the timing of occultations or blocking of specific stars from multiple locations were all used to try and calculate the size of the moon and its distance away from Earth. The next big step comes in the 1940s, where the U.S. Army Signal Corps began a project known as Project Diana. The goal of Project Diana was to bounce radar signals off the moon and receive the reflected signals back on Earth. Now, their success came in January 10th of 1946. You can see the newsprint on the left there of this attempt, as well as the image of the radar dish that they used to make the measurement. On the right-hand side is a plot of essentially You can think about the bottom axis as time and the top axis as the strength of the signal, and you can see they received a strong signal at about 238,000 miles away. So not only did this allow for the first precise measurement to about a precision of a couple miles or so to the distance between the Earth and the Moon, it also demonstrated an extremely important fact that had never been proven, which is that radio signals can penetrate the ionosphere of Earth, or the upper atmospheric level. And that makes communication with space probes and human explorers possible. This was not something that was taken for granted before these measurements were done. It also marked the birth of radar astronomy, which was later used to map the surface of Venus and other planets. This technique was improved over the next several decades, resulting finally in a precise range to within about a mile or so in the late 1950s. Now, in the early 1960s, scientists and engineers switched to using a relatively new technology of lasers, and the plan was developed by a graduate student, in fact, to deliver a series of specialized mirrors to the surface called retroreflectors. So what is a retroreflector? You heard Stacy use this word. A retroreflector is a special kind of mirror or prism, and what it does is it reflects the light back in the exact direction it came from. So that's shown by the image in the upper left there. Now, a traditional mirror will just bounce the light at the same angle it comes in, and that's what's shown in the lower left there. But these mirrors send it back in the exact same direction it comes from. Now, this same phenomenon is used in road markers, as shown in the upper right. So those use special glass beads to retroreflect the light from your headlights back directly to your car and give you clear markers with which to drive. The same technique, or the same phenomenon, also occurs in cat's eyes, which is why some of these road markers are also called cat's eye reflectors. So the Apollo 11 mission actually distributed one of these retroreflector arrays on the moon. You can see several images of the retroreflector array being carried out to its placement location and placed on the surface. So this array was about the size of a briefcase or so, and it contained 100 of these special retroreflector prisms. They look like holes, but I promise you there is special glass prisms within each of those holes, and it was placed on the surface facing directly back towards Earth. What scientists then did is they used very powerful lasers on the Earth's surface to shoot at the moon, hit that very special mirror about the size of a briefcase. The light was then bounced directly back in the same direction, and they used a telescope to see that light on Earth. They then recorded the time that they fired the laser and the time that the light came back to Earth. And since we know the speed of light to a very precise value, we could then determine the distance between the Earth and the moon. Now, over the next several years, 4 more of these retroreflector arrays were placed on the surface of the moon, as shown on the map on the right. So as I said, the Apollo 11 mission, also the Apollo 14 and Apollo 15 missions delivered retroreflector arrays to the surface, and also the Soviet Lunar missions delivered 2 extra arrays to the surface. One interesting story about the Lunar array: the second array that was delivered on the Luna 21 mission was actually lost. The precise location of the array was never recorded, and the files were lost in the fall of the Soviet Union, and so this retroreflector array was essentially missing on the surface of the moon. They knew roughly what location it must have been in, but no one had ever confirmed that it was there or ranged to it with a laser. Finally, in 2012 or so, a group was successful by doing a very painstaking search with their laser itself of the surface to find the array, and now it's been added back into the catalog of laser retroreflector arrays that can be used for measuring this distance between the Earth and the moon. So what have scientists done with this information? They've been doing these measurements continuously over the last 56 years or so. Well, the first is they've demonstrated an unbelievably precise range measurement. So this is one of the most precise distance measurements that's been ever been made. You can think about it as the equivalent of measuring the distance between Los Angeles and New York to the precision of about a human hair. The other thing it did is it discovered that the moon is actually spiraling away from the Earth at the rate of several centimeters per year. And so what this means is that scientists could take that information and then turn back the clock to discover when the Earth when the moon formed, how close was it to the Earth, and what would that have done to the length of a day? And what they determined is that the day when the moon formed, a day was about 4 hours long, which made almost 2,000 days in a year, which is pretty amazing. Now the moon is continuing to spiral away from us at this rate, and the day is still getting slightly longer. None of us will probably feel its effects, but those who are here millennia from now will look back on our 24-hour days as quite brisk. And finally, they've proven that these retroreflector arrays can provide very accurate reference points for both orbiting spacecraft and essentially setting up a reference system on the moon. So where do I come in? Well, I've been working on a project for the past 7 or 8 years now to build miniaturized versions of these arrays. So these are our miniature laser retroreflector arrays that we've been building at NASA Goddard Space Flight Center. And we built these to go to the moon on a series of lunar landers. So under the Commercial Lunar Payload Services program run by NASA, commercial companies have been sending lunar landers to the surface over the past several years, along with international partners such as the Japanese Aerospace Agency, the Indian Space Research Organization, and the Chinese Space Research Agency. And these retroreflector arrays are not able to be measured from Earth, but they are able to be measured from spacecraft around the moon. And that gives those spacecraft a very precise marker on the lunar surface that does not require any power. It doesn't require any special considerations from the lander. It simply sits there and reflects the laser light right back. And I actually brought with me today one of the laser retroreflector arrays. This is not one of the flight versions, but this is a mock-up that we made. And so you can see the size of it. You can see the retroreflector prisms inside of it. If you look into the prisms, what you might see is a little blue light. That little blue light is actually the light from my camera reflecting right back to the camera. So the camera can only see itself when it looks into the prisms, and that's exactly this concept of retroreflection. And so some of these images here are these retroreflector arrays under test at NASA Goddard. In the upper left there, those retroreflectors are about to go into what's called the thermal vacuum chamber, and that is a test that we use to simulate the lunar environment to make sure that our hardware will survive the lunar night. The lunar night actually gets quite cold. It gets down to around minus 170 Celsius on the surface of the moon at night, and during the daytime it can get up to about 100 Celsius. And so we need to put these retroreflectors through incredibly stringent testing on the thermal side to make sure they'll survive. On the right-hand side there, that's a vibration test fixture, and that's to make sure our hardware will survive the stress of being launched on a rocket. There can be quite a lot of vibration, as you might remember the Apollo astronauts commenting on their way to the moon, and we want to make sure our hardware will survive that. And then finally, in the lower right there, we're shining a laser on it to measure exactly how much light we get back to figure out what kind of signal we expect from these arrays when they're on the surface. So these are a few images of the arrays that we've sent to the surface on international missions. The upper left there is a private mission from Israel, the Space IL Bereshit mission. Also the ISRO, which is the Indian Space Research Organization, Chandrayaan-2 mission, and the Japan Aerospace and Exploration Agency SLIM mission also carried one of our LRAs to the surface. Now these miniature LRAs are quite valuable. Despite not needing any power or providing any data themselves, they act as a combination of a lighthouse, a landing light, and a geodetic survey marker. So you can think about the spacecraft brings along the light source, and the retroreflector acts as the beacon on the surface when it's hit with that laser. And if you place several of these around a landing location, you can use them to orient yourself in dark conditions. And again, these will stay on the surface and survive for decades, just like the Apollo arrays have. And so they will act as permanent markers on the surface that can be used to navigate spacecraft around the surface. So this is a map of where on the left is the number of retroreflector arrays on the surface between 1973 and 2019. Again, it's those same 5 that I mentioned before. And on the right-hand side is a map showing what we're doing with these small laser retroreflector arrays. So We're greatly increasing the number of arrays on the surface. We're placing these on essentially every CLIPS mission that's going to the lunar surface. There's a lot of excitement about exploring the south pole of the moon, which you can see by the density of missions on that lower globe. And part of the reason why these retroreflector arrays are so valuable at the south pole is that the illumination conditions are incredibly challenging. So what I'm about to show you is a video of the simulated illumination conditions at the south pole of the moon over one year. So to give you a reference, that very circular crater right in the middle is Shackleton crater that's very near to the south pole itself. And because the moon essentially has rotates directly on its axis without any sort of tilt, at the poles, the sun is essentially always at the horizon. And so you can see those dark the regions inside some of these craters are permanently dark, and those are called permanently shadowed regions. They're of immense exploration and science interest because these permanently shadowed regions stay cold on the timescales of millions or potentially even billions of years. So anything that falls into those craters and gets trapped there by the cold will still be there hundreds of millions or billions of years later. So we think that exploration of these very cold, very dark places will give us hints about things that may have been delivered to the Earth-Moon system, such as water or carbon dioxide very early in their formation. If there was potentially any biological material delivered to the Earth-Moon system early in its formation, we may find remnants of it, such as organic molecules there. But the other thing that makes it so challenging is that trying to navigate this kind of area with visual imaging or your eyes alone. I mean, it's so incredibly dark. And so something like this retroreflector array will light up underneath a laser illuminator. And so you can think about using these to navigate in the dark, just like you would use road markers to drive on a very dark road during nighttime. Okay, so I wanted to jump a little bit ahead here to a very exciting part of lunar exploration that's currently ongoing, and that is the Artemis program. The Artemis program, for those who don't know, is NASA's newest program to return humans to the moon and to return them there for long-term habitation and eventually the construction of some sort of lunar science base at the lunar South Pole. So this program started with the Artemis 1 mission, which happened several years ago. I just want to play this video of the launch of the rocket because it's just so cool and gets me really excited. You know what? I forgot to turn on sound. Let's fix that.
I was just going to say, thank you.
It's the one thing I forgot. Okay, let's try it again. That's okay. Please excuse me for a second. I need to stop my slideshow and start it over. All right, here we go. With sound this time. Apologies, everyone. So we'll skip through this and we'll get back to our fun Artemis launch. All right, hopefully we get sound this time.
And here we go. 10. Hydrogen burn-off igniters initiate. 7, 6, 5. 4-stage engine start. 3, 2, 1. Boosters in ignition. And liftoff of Artemis 1. We rise together back to the moon and beyond.
For those of you familiar with the Saturn V rocket, this rocket was more powerful than the Saturn V.
128 miles per hour.
So this was the first Artemis mission. This did not carry any humans aboard. It was a test of the new SLS rocket and the Orion capsule, which touched down safely back in the ocean several weeks later. You can see the photo on the right there. Now, the next mission, which is coming up very soon, April of next year, is the Artemis II mission. And this is the first Artemis mission to carry human astronauts. They will be doing a trip around the moon, very similar to the Apollo 10 mission. And these 4 astronauts will be the first astronauts outside of low Earth orbit since the Apollo 17 mission. So this is very exciting. And it's leading up to the Artemis 3 mission, which is scheduled for 2027, which will be return of humans to the moon for the first time in, it will be about 60 years at that point. And so it's very exciting. The scale of the lunar lander you can see on the left there is going to dwarf anything that came down in the Apollo program. There's a lot of exciting science to do at the South Pole, including looking into these permanently shadowed regions and also finding places to begin large-scale construction of things like landing pads, habitats for long-term habitation on the surface, and also setting up things like surface power stations. So the last thing I wanted to bring up today is I wanted to put in a plug for a very exciting event coming up called International Observe the Moon Night. So I'm going to play this video, and then maybe Stacy can give a little pitch, and then we can take some questions.